what we're going to talk about today. We're going to review mechanisms. We're going to do some mechanism practice. Then we're going to introduce y'all to alkene reactions, and we'll do some alkene reaction mechanisms. So this is the first one, nucleophilic attack. It's where a nucleophile attacks an electrophile. And remember, a nucleophile is one that is electron rich, and an electrophile is one that is electron deficient. Then we have a loss of leaving group. This is when a good leaving group is able to leave the structure. As we see here with bromine, it's able to leave these carbons. And we got proton transfer. This is simply when a proton is transferred from one molecule to another. And we got rearrangement. And there's two types of rearrangement. We have the hydride shift and we have a methyl shift. Don't forget that there are these two. You'll most often do a hydride shift, but sometimes they'll throw in a methyl shift to throw you off. So don't forget about it. And do some mechanism practice. We'll have y'all label each step of the mechanism using those four patterns. All right, let's go over it. This shouldn't take you very much time. It's just recognizing the patterns and writing them down. So the first thing we see, always compare your reactants with your products. We see that our reactants look like that and our products look like that. The thing that is different is that there is this hydrogen here. What is the name of the pattern where hydrogen jumps from one molecule to another?
It's a hydrogen that's being shifted. So what would it be?
Yes, there's a proton transfer. Hydrogens are very commonly called protons because when a hydrogen has one proton and one electron. So when a hydrogen loses its one electron and becomes like an H plus, that's just the proton. So hydrogens are commonly called protons. People often call them protons, but don't really explain why. That's why. And then in the second step, we see that the bromine with a negative charge is going towards this positive charge. Do we know what that's called? We have something electron rich going to something that's electron deficient. Yes, that is nucleophilic attack, and this was the leading group. You look confused. You have a question? Or not leading group, my mistake. That is a proton transfer. I see why you're confused. Yes. Answers. All right, we're gonna do that again. Give you all a couple minutes on this, and then we'll go over it. All right, let's go over this. So the first thing is we're looking at this. This is a nucleophilic attack followed by a nucleophilic attack. There's two nucleophilic attacks going on right here. So the way that looks is we got this alkene, we got the bromine. When it breaks its bond with this, it becomes like a little bit positive because it's losing some electrons that I was previously sharing with the bromine. So this goes and picks it up. Kind of looks like something like this. But there's still electrons on this bromine. So it can do another nucleophilic attack right there on there to form this. Does that make sense? There's two nucleophilic attacks going on right there. And then in the next step, when this breaks, it basically is forming something that looks like that. That looks like that. So then this bromine can go and attack there where that positive charge is and form this product. That's another nucleophilic attack. That's basically as hard as it's going to get. I remember there was a quiz when I took this and there was a problem that looked like this. Yes. Like you're talking about that?
Technically,
Yeah, is like you could label this as a leaving group, but that's not like the important part because that's not like what is happening in the product. Yes.
Yeski said it was a leaving group.
I mean, yeah, you could call it a leaving group. It is leaving right there, I guess. Jessica has final say on this, so obviously do what he wants, you know. If you have like specific questions like that, it'd probably be best to ask him what he would want from that. So answer. And we got another one. I'm gonna label each step of this mechanism. All right, let's go over this. So we see right here, it's picking up that hydrogen. Another name for our hydrogen is a proton. Do we know what that's called? Yeah, proton transfer, good. And then in this next step, we see a oxygen that is electron rich. It has those lone pairs. It's going towards an electron deficient spot. It's a nucleophilic attack. And then this last step, do we know what that's called? Proton transfer. Yes, the proton is shifting to another molecule. Seems like you are getting this. All right, this one's gonna have you draw the product of this step right here.
It's very similar to one of the mechanisms we just saw.
So let's go over this one. So we see that this bond is breaking right here. And that looks like that. And then we have the oxygen going to that spot. So it looks like that. Makes sense?
Is this intermediate or does this happen at like once?
Um, I don't know. Maybe at once, probably at once. I'm just showing them like what it looks like. We're gonna label these steps too. Do we know what this first step is called right here? Said nucleophilic attack. How many of them? Two of them, yeah. Because we have that double bond attacking the bromine, and we also have that bromine attacking that carbon. And then this second step, do we know what that's called? You know what this is called right here?
Electron rich. What was it? Not really. There's no proton that's being transferred, but we see that it's electron rich attacking electron deficient. So what that be?
Yes. Nucleophilic attack. All right.
So the cation, if he gave it to us without the arrows, could you have it, the BR going to the top?
Yep. Mm.
Okay. Okay.
Unless there is like substituents. Like if there's a substituent here, right? The OH would have to go on the more substituted side. But if it's the same on both sides, it doesn't matter. You can go on either side. All right. I'm gonna have y'all draw the mechanism of this. Pretty similar to what we did on the last question of the quiz. All right, let's go ahead and go over this. Pretty much the exact same question as the one that was on the practice quiz. So first thing that we do is we have this proton transfer right here. And that forms this, right? And then we still have this chlorine with the negative charge. that was formed from this step. It can attack that with a nucleophilic attack. To form this as our product. When you're doing this, you want to add the hydrogen to the less substituted side, but both of these would be secondary cations, so you can add the hydrogen to either side. But they've also got this as a product. Thumbs up if that makes sense. Thumbs down if it's like kind of iffy. Thumbs up. All right, cool. So, all right, I'm gonna have you draw the mechanism of this reaction. All right, let's go ahead and go over this. So first step, we're gonna do a proton transfer like that, and that will form this. And then that also has us with an OH2, like that. And then this OH2 has electrons. I can do a nucleophilic attack to form this. And then we see that we have a positive charge on this oxygen. It would be better if we didn't have that. So we have this H2O right here. The H2O can do a proton transfer on there to form this. So it had the plus charge because it had 3 bonds to it. The H2O picked up one of those bonds for the hydrogen, and yeah, the electrons from that bond went to the oxygen, getting rid of that plus charge. Mechanism. All right, everything we just shown was an alkene reaction. So typically in an alkene reaction, the double bond will attack an electrophile, and that will form a cation, and that cation can then be attacked by a nucleophile. This is the general mechanism of alkene reactions. All right, and then this is the regioselectivity. This is what I was telling you about. So when you have just HBr, the Br is going to go on that more substituted side. And then if you have HBr and say peroxides, if it will either say peroxides or it'll write out ROOR, that's also peroxides, it's going to make the anti-Markovnikov, which will put the Br on the less substituted side, like that. Right? So if a reaction is anti-Markovnikov, it goes on the less substituted side. And if it's Markovnikov, it will go on the more substituted side. Put the group on the substituted side. Some reactions prefer one over the other, and we'll cover that. There can also be syn or anti. Syn is them on the same side. Anti is them on opposite sides. Pretty easy to remember, anti, opposite, you know. And we see syn addition in this, with OH both coming towards us. They're both on the same side. And then we see anti with this Br2, we have one Br going up and one going down. So they're opposite, they're anti. This is pretty much the general mechanism. Already covered this. So this is the first one. It's called hydrohalogenation. It can be done with HBr or like HCl. Those are the ones you'll see most commonly. And the way it works is the double bond picks up the H, forming this chlorine and that. And then the chlorine attacks that to form that. And this is Markovnikov, no peroxides or anything, so we know it goes on the more substituted side. And we have this intermediate of the carbocation. What it looks like. All right. Do we think that this will form A or B? Thumbs up for A, thumbs down for B. All right, I see some thumbs up for A. So this is HBr. We know that it's going to go, the Br will be on the more substituted side. So it could either be here or it could be here of the alkene. And there's no peroxides, so we know it goes on the more substituted side, making the answer A. Okay. And then when you have two halogens, like Br2 or Cl2, they across the alkene, they'll be anti. So it forms this. And it can be, can also form this. It's doesn't really matter. It can be either one of those. And the intermediate is a halonium ion. We'll see that in a second. Looks like this. Right? This is the bromonium ion. So we see that double nucleophilic attack at the start. It forms this bond right here to the bromine. This could also form like, could also be this, doesn't really matter. And then we have a bromine come and attack one of those, and it would form an anti-configuration. You see that here. Predict the mechanism. Can we draw the mechanism for this? I'll go through this with y'all. So when you see a Br2, Cl2, you're gonna want to try and form that little triangle looking thing with the bromine, the bromonium ion. So first thing that's gonna happen is this goes here, and this will attack there, right? And that will form, don't forget to break this bond. That will form that little triangle, bromonium ion, positive charge on the bromine. And then from there, the bromine that was from this right here, it's the same bromine. It will come and attack one of these bonds, breaking that, going back to the bromine and forming this. Which one? You're talking about like these ones and coloring in? Yeah, they're both going to the bromine. It forms that little triangle looking thing with the bromine called a bromonium ion. I believe I made a mistake on this one. So With that second ion, you want it to attack the more substituted side. So it attack there, and this would actually form this. The reason that this is different because instead of drawing it like this, they drew it like this. You can draw it either way. It doesn't really matter. Key. Remember that second bromine ion wants to attack the more substituted side. This is the halohydrin formation. We saw the mechanism for this. We drew it. So typically how this works is that the bromine will be attached to the less substituted side, and then you'll have an OH or an OR group on the more substituted side. And we see that with this, right? Bromine on that less substituted carbon, and the OH on that more substituted carbon, or it's OMe in this case. And again, the intermediate of this is the polonium ion. So for this case, it would look like that. That is the intermediate. Another case, instead of Br2, you can also use NBS. NBS also will add that bromonium ion. So the mechanism, we drew this earlier. All right, now let me draw the mechanism of this reaction. Just for a hint, this is what MBS looks like. All right, let's draw this one. So first thing we're going to do is we see that as MBS H2O. This is a halohydrin reaction, and we know that it forms a bromonium ion intermediate. So let's form that. We have this attacking here. I have this attacking here, two nucleophilic attacks. And we get this intermediate, the bromonium ion. And then from there, we have the H2O. This has lone pairs on it. This can attack here, breaking this bond. When you're doing this, the H2O or the OH or the OR group, it will always attack the more substituted side. So we see we have a tertiary cation versus a secondary. So it's going to attack that tertiary, and that will form that. And then we want it to look like our product. So we have that H2O, another one. I'll pick up one of those hydrogens, do a proton transfer to form this product.
What the second H2O?
Typically when there's H2O, it's in excess. There's a lot of it.
What makes the bromine wedge flip to like the other side, like so it's going down?
I mean, it could be on the top, but it looks better like that.
But it flips like that because the oxygen is going to the one with the better substituents.
Mhm.
And remember, this reaction is an anti-addition instead of syn addition. So one of your nucleophiles is going to be on the backside on a dash, and the other one's going to be on a wedge.
Yeah. make sure they're anti, so they're opposites. It could also get this as a product, as long as they're anti.
Yeah, so for these alkene reactions, you're gonna know you got to memorize like 8 of them, and you're gonna have to memorize if they have stereo selectivity, meaning if they're gonna be anti-Markovnikov or Markovnikov, and then you're gonna need to know regio selectivity, if it's going to be syn or anti-addition, and then the third is if there's any intermediates, if it's going to form any carbocation intermediates or halonium ion intermediates or like a ring like this, you'll need to know those three subcategories.
It's just some stuff you have to memorize, but if you practice it enough, it'll come naturally. It's that mechanism. There's another one. We have acid catalyzed hydration. And this one is just going to put an OH on the more substituted side of the alkene. So we see that here. It also puts a hydrogen on the other side of the alkene. That's typically not shown. And the intermediate for this is a carbocation. Again, for this example, this would be the intermediate. Here's the mechanism for this. You typically start with a strong acid like H2SO4. The H2SO4 is deprotonated. There's a proton transfer. So that H is right there. And then it has the cation there attacked by the H2O. And then the H2O is deprotonated to put an OH on the more substituted side. All right, for this one, draw the product. And then tell me if it is a carbocation, if it's Markovnikov or anti-Markovnikov, and then if it's syn or anti.
It'll probably be easier if you identify if these have the 3 requirements there first, and then draw the products, because those 3 things affect how your products might look.
All right, let's go ahead and go over this. So H2SO4, H2O, we know that that does form a cation as its intermediate. So yes. We know that it is Markovnikov with an OH going on the more substituted side. This is a yes. And then it could be syn or anti. So drawing the product of this, we know it's going to put an OH on the more substituted side, but we also know it forms a cation. And something you always want to look for when you have a cation is if it can do rearrangement. So in this case, when we add that hydrogen, we get the cation there. This cation can do rearrangement. We have that H there. We can do a hydride shift, and that will give us this cation, right? And then we can put the OH onto there. So our product would look like this. Make sense? You understand that? OH goes on the more substituted side, forms a cation intermediate when you have H2SO4 H2O.
So how do you know which parts of the H2SO4?
I mean, you can go back and look at the mechanism. So H2SO4, it looks like this.
That just one that's gonna show up a lot.
What do you mean? Like the mechanism?
Or yeah, like you only use like the OH from it.
Yeah, so H2SO4 is like generally a really strong acid. And for this, you want a really strong acid, so you want like the whole molecule. Yeah, specifically H2SO4 too. Yeah. This is a mechanism you should know. This is something we got tested on like when we took the class. Yeah, that's all we got for today. Scan this, give us feedback. We'll listen to you. We'll do better next time if you want us to.